Okay, chemists, in this video we're going to go through the 2017 exam question 2. This exam covers topics related to structures, as well as some thermochemistry, and even a little bit of kinetics. There's a variety of topics squished into this question, so let's look at it. The first one has us look at these two Lewis electron diagrams for fulminic acid. These happen to be resonance contributors of each other. And it says, explain why the one on the left is better, justify in terms of formal charge. You got to look out for when they say justify. That means there's definitely going to be something awarded for giving some kind of explanation, probably conceptual. And they're usually pretty specific about what they want you to talk about in your justification. So this one is all about formal charge, which means let's review very quickly what formal charge is all about. Formal charge is the valence of an atom minus the bonds it's making minus the dots that are on that atom in the molecule. So if I look at one of these, hydrogen you hardly ever have to worry about. Hydrogen has a valence of 1. It's making 1 bond and it has 0 dots. So this has a formal charge of 0. We don't even write it. Carbon right here has a valence of 4. It's making 4 bonds and it has 0 dots. So it also has a formal charge of 0. But when I get to the nitrogen has a valence of 5. It's making 4 bonds and there are 0 dots. So this actually has a +1 formal charge on the nitrogen. Likewise, oxygen, valence of 6 minus 1 bond minus 6 dots. This has a -1 formal charge. Take a look at the other resonance contributor on the right. Hydrogen, nothing. Carbon has a valence of 4 minus 3 bonds minus 2 dots. That means carbon actually has a -1 in this structure. Nitrogen will still be +1 and oxygen will be 0. So we're essentially comparing the negative charge of -1 on an oxygen versus a -1 on a carbon. And that's the key. Oxygen is more electronegative than carbon, so it's going to want to have the negative charge. Therefore, the structure on the left is the preferred structure. So let's now write an answer. It's part A. The left structure is preferred because negative charges prefer to be on more electronegative atoms. And I'm going to underline that more electronegative part because I really think that's key. On the left, O is -1, but on the right, C is -1. And this was a 2-pointer. We had to first comment on what some of the formal charges were, really highlighting carbon being -1 versus oxygen being -1 in the two structures, and also justify why the more electronegative atom prefers the negative charge, or the fact that it does. And that's part A, that's 2 points. B, using these electron dot diagrams for a hypothetical reaction of something called fulminic acid going to an isomer, isocyanic acid, determine the value of delta H for this reaction. Anytime you see bond energies and structures and you want to get delta H, it's very straightforward. Delta H is simply the broken minus the formed. So we need to tally all the bonds that are broken and all the bonds that are formed. We break everything in the product. So we're going to break an HC bond. We're going to break a CN triple bond, and we're going to break an NO single bond. And then we're going to form, I'll actually put that all in brackets, we're going to form and release energy from the HN bond the N-C bond and the CO double bond. That's just me looking at the structure of each reactant and product, just sort of left to right. CH, CN, NO, and likewise on the right-hand side. And they give us all the energies. We simply have to plug them in and write an answer. So the CH bond, single bond is going to be 413. The CN triple bond is 891. Make sure you use the triple for this one. The NO single is 201. And then we subtract the sum of the NH, 391, the CN double, which is 615, and the CO double, which is 745. And you get a numerical value of negative 246 kilojoules per mole of reaction. This is also a 2-pointer, 1 point for the correct numerical answer, and then 1 point for some work showing the method of bond energies used to calculate delta H. Okay, moving on. Part C. A student claims that delta S is 0. Explain why the student's claim is accurate. Looking at a chemical reaction, you can always approximate delta S by looking at the changes in phase. Well, here we have no change in phase, and we don't even have any changes in particles. So we have one gas becoming one gas. So we would guess that delta S for this is actually pretty close to 0. So that student's claim is accurate. The reaction involves no change in phase or number of particles. So delta S should be pretty close to 0. And that's just a 1-pointer, offering some explanation as to why the entropy is expected to not change that much. And then we're off to part D. D, still talking about thermochemistry stuff. Which species, the fulminic acid or the isocyanic acid, do you think is going to be in the higher concentration when we're at equilibrium? Justify in terms of thermodynamic favorability. Thermodynamic favorability and the equilibrium constant make me think of things related to delta G. That's what I'm trying to imagine. And since this is part D, a good tip is think about what they just had you do in the previous parts of the question. I'll bet they want us to use those somehow to come up with an answer for this later part of the question. And it's all about the combination of delta H, which we just talked about, and delta S, which we just talked about, and how they combine for delta G. So first of all, let's recap what's true. Delta G is equal to delta H minus T times delta S. And we just said that delta S is roughly equal to 0. So this second term is essentially 0. So I'm going to write is approximately equal to delta H. And if delta G is equal to delta H, that means delta G is this negative number. Delta G negative, that means equilibrium is big and products are favored. So because delta G standard is equal to negative 246 kilojoules per mole, or really approximately equal to, the reaction is favorable, meaning thermodynamically favorable, and KEQ will be large, greater than 1. Thus, the product, HNCO, is present in higher concentration. Okay, that's just the first first half of this. We still have the kinetics portion of this, the second half of this fairly lengthy question. Well, let's take a look. The ammonium salt of isocyanic acid is the product of the decomposition of urea, shown below. A student is studying the decomposition reaction. They collect data of concentration versus time. Here we go. This is kinetic information. The student proposes the rate law looks like this. Rate equals K, concentration of urea to the first power. Explain how the data support the proposed rate law. Well, what would they want us to know about a rate law and looking at the data? This is a first order process. So we need to be able to figure out from the data why this is first order. The easiest thing to do is to look at the half-life. And when you're looking at a graph like this, you can easily find the half-life by starting at the beginning and noting where it gets cut in half. So 0.1 molar initially goes down to 0.5 molar at, it looks like, exactly 10 hours. And then you could keep going. A 0.5 molarity will get cut into 0.25. And from the first 10 hours, that takes an additional 10 hours. In fact, that will get cut down into 0.125. And it's a little bit higher than that, isn't it? And it looks like that lines up right where the next 10 hours happens to be. So this is an exponential decay, but the amount of time in between each segment where it cut in half is exactly the same. And that's true for any first order process. So let's make some room and write the answer to part E1. So E1. The rate law is first order based on the data which shows a constant half-life. And that's really it. This is a one-pointer. It's very common that the AP wants us to know that a constant half-life is always true for first order. I probably could have written this even faster. Let's go on to the next one. Speaking of, I can tell the next part's going to be related to the previous part. Using the proposed data, determine the value of the rate constant. Include the units. Maybe you weren't sure what to do about part one, but then once you got to part two, you were like, oh, I want the rate constant, and it's a first order reaction. Rate constant is related to half-life because K is equal to the natural log of 2 divided by the half-life. That's true for first process. That's on your reference table, but some students just already know it. So part 2. Calculate the rate constant, K, is ln2 over the half-life. ln2 is about 0.693. The half-life, according to the graph, looks like 10 hours every single time. You can actually do this without a calculator, and I get 0.069 inverse hours. This was unfortunately just a one-point question, but it's a pretty easy one, so not too surprising. Note for rate constants, that is the one time that you can guarantee the graders are going to want to see your units. Always include your units for a rate constant because they're really dependent on what your units are in for the half-life if you're using this formula. They're also very dependent on just what the order of the reaction is. First order reactions, second order reactions, third order reactions, they don't all have the same units for the rate constant. Make sure you include units. Okay, we're almost done. Last part, the student learns decomposition was run at a pH of 13, very basic. Describe an experiment, including initial conditions, that you would change to see if the rate actually depends on the concentration of hydroxide. Anytime they say describe an experiment, they're really looking for one or maybe two specific things that they want you to say, but they're usually pretty straightforward. They just want to hear from you that you know that that's all you have to do. And in this question, that's what it is. The pH is 13, and I want to change something to figure out if the hydroxide concentration is a variable. You just change the hydroxide concentration. So part F is unbelievably straightforward. So perform an experiment that has a different concentration of hydroxide. I'm going to abbreviate that. And measure concentration of urea versus time again. And that's just one point for mentioning essentially different hydroxide concentration. That's all they really wanted you to say. Okay, so that's all the parts of this question back from 2017. Total of 10 points that are distributed among the parts, and a good review of kinetics, thermochemistry, and some structures. Thanks for watching.